Alright, welcome back everybody. In this video we're going to look at finding intervals of convergence of series. We've mentioned before this concept right here that a series can have one of three possibilities: that it converges only at the center, that it converges in a finite interval around the center, or that it converges for all real numbers. In all of these situations, the series converges absolutely in the interior of the interval of convergence. So when it converges for all real numbers, that means that it converges absolutely for all real numbers. When it converges at only at the center, it converges absolutely at the center and diverges everywhere else. When it converges on a finite interval, on the entire interior of the interval, it converges absolutely. But at the endpoints, it's possible that the series could converge absolutely, it could converge conditionally, or it could diverge. So now we're going to dig into how we actually find full intervals of convergence for infinite series, which is going to require us to do a couple of things. The first thing we're going to do is use the ratio test to find the interior of the interval of convergence. And then if it's a finite interval, we've got to test at the endpoints and see if those endpoints converge or diverge. So let's get into it. Let's look at example 1 here. We're going to find the interval of convergence of this series, and then after we find the interval of convergence, we're going to determine the values for which a series converges absolutely and converges conditionally. So the first thing I'm going to do is set up the ratio test here to find the interior of the interval of convergence. So I've got the limit as n goes to infinity of the absolute value of -1 to the n plus 1 times n plus 1. I'm going to run myself out of space here. Let's try this again. Write a little lower. Come on, eraser. Come on. You don't want to erase? Fine. Sorry, I guess my computer's being cranky this morning. So we'll set up our ratio. The limit as n goes to infinity of a sub n plus 1 times the reciprocal of a sub n Okay, and simplifying this turns into the limit as n goes to infinity of the absolute value of -1 times the quantity x plus 3 all over 4 times n plus 1 over n. And as n goes to infinity, this portion approaches 1. So in reality, this turns into the absolute value of x plus 3 over 4. Now, in order for this to converge by the ratio test, this has to be less than 1. And so I set up the inequality and I solve this inequality. I've got -4 is less than x plus 3 is less than 4. Subtract 3 from both parts, and I'm going to kick myself up to the top here. I've got -7 is less than x is less than 1. So there's my base interval of convergence. Now, I need to test what happens at the two endpoints. At x equals -7 and at x equals 1. Okay, so at x equals -7, I'm going to substitute -7 into my original series, and that becomes -4 to the n times -1 to the n times n. And if I simplify all of this, what it ends up turning into is the sum from 1 to infinity of n, which diverges. And so this endpoint is not included. At x equals 1, if I substitute 1 in there, this turns into the sum from 1 to infinity of -1 to the n times n, which again, this time by the alternating series test, this diverges. And therefore, in my interval of convergence, neither of the endpoints will be included, and so my interval of convergence is going to just be from -7 to 1, excluding the endpoints. And then to answer questions A and B, it converges absolutely everywhere in the interior, and there are no other points in the interval of convergence other than the interior, so it converges conditionally nowhere. Alright, that's the end of example 1. Example 2, find the interval of convergence of the series, then determine the values of x for which the series converges absolutely and converges conditionally. I'm going to start by using my ratio test to determine the base interval of convergence. So I've got a to the n plus 1, or a sub n plus 1, pardon me, times the reciprocal of a sub n. And when I simplify all of that, let's see, this is going to turn into the limit as n goes to infinity of, and I end up with a 2 in the numerator and a 4x minus 8 in the numerator times n over n plus 1, which is equal to the absolute value of 2 times the quantity 4x minus 8. In order for this to converge, that absolute value has to be less than 1. So I set up my inequality here. And solve this inequality. Add 16 to all the parts. So there's my base interval of convergence, and now I need to examine what happens at the endpoints. At x equals 15 over 8, and at x equals 17 over 8. At x equals 15 over 8, I put 15 over 8 in here, and that gives me, let's see, if I put 15 over 8 in here, that's 60 over 8. That's 15 over 2. That gives me -1/2 to the n inside here. Gives me -1/2 to the n. If I multiply -1/2 to the n times 2 to the n, this simplifies to -1 to the n over n. And if I put 17 over 8 in here, this simplifies to 1 over n. This converges by the alternating series test. This diverges because it's a p-series. See how all these, different properties we've learned, all these different tests that we've learned come into play, in different spots in each of these problems. So it's really important that we have all the tools available to us and really know all those tools to show these things. So it converges at the endpoint 15/8, which means my interval of convergence is going to be 15/8 is less than or equal to x, which is less than 17/8. It diverges at that endpoint. And so what we have here now, where does it converge absolutely? Well, realize that if it converged absolutely here, this endpoint would also converge. And so it doesn't converge absolutely there. It in fact converges conditionally at x equals 15/8. And then everywhere else in the interval of convergence, it converges absolutely. All right. That's where we're going to call it quits for today. We'll come back in the next video and look at examples 3 through 5 from this lesson on finding intervals of convergence. See you guys next time. Have a great rest of your day.